Hello everybody, my name is Ricardo Rocha. I'm presenting lab number 4, which is about oscillations. Well, for this homework I had to use the basic code that I wrote from the previous lectures, where in that case I consider a spring mass system moving in one dimension, only on the y-axis. For this homework, we had to consider the object moving in two dimensions, on the x and y axis, as we can see here in the video on tracker. We can see that the object is oscillating up and down as it oscillates on the x axis from left to right. The motion obtained looks like an elliptical orbit, like this. So from tracker, we can see the initial x and y position. Then I can obtain also the total time for my loop, which is 9.3 seconds. We can see that the object oscillates on x and on y. From this information in tracker, I can answer the first question, which asked me about the period of oscillations. So what I did is I tracked point by point, step by step. So when I went back to the initial position, looking at the x versus time graph, I could see that the period of oscillation is approximately 1.61 seconds. It doesn't match perfectly with the time in the y versus time graph. So according to my y versus time graph, the period should be 1.51. The difference is minimal, but there is a difference because of my clicking. Maybe I didn't click so well here, but the period is about 1.5 or 1.6 seconds. The difference is minimal. It's almost negligible. Okay. So with this information, I went to VIDLE when I run my first model. In order to run this model, I had to define first the mass of the ball, the initial position with the x and y coordinates given in tracker. Then I had to define, well, all the previous things: acceleration due to gravity, j hat vector. The new things that I had to define were the spring constant, the initial length, the final length vector, the L hat vector, and the magnitude of S. Then when I come to my loop, I use a time of 9.3 seconds. I had to use Newton's second law to update the spring force, the net force, and the ball's position and velocity. Then I also had to update, obviously, the final length, the L vector, and the S magnitude. So when I run this model, I'm very sorry if it is a little jumpy. It's not very fluid because my computer is a little slow. So here I will see the motion. Here we can see the blue ball. Here we can see the spring. In the blue arrow, we can see the spring force. In the black arrow, we can see the weight. And in the red arrow, we can see the net force. Here I also graphed the x versus time, and here we can see the y versus time graph. We can see that the amplitude here on the x-axis is bigger than the amplitude on the y-axis because it moves more on the x-axis than on the y-axis. So this is the first part of the homework. Then another questions that we had was about the energies. So first I defined my kinetic energy, my gravitational potential energy, and my elastic potential energy. Then inside the loop I had to define the initial energies. Then I had to update the kinetic energy, gravitational, and elastic potential energy, and I also had to define the changes in kinetic, gravitational, and elastic potential energies. With all these updates inside the loop, I could come and graph the energies, as we will see here. Okay, here we can see that the blue line stands for the change in the kinetic energy. The red line stands for the change in the elastic potential energy, and the green line stands for the change in the gravitational potential energy. The most important part in this graph would be the yellow line, which shows the change in the total energy, or the change in the mechanical energy, which in this case is always 0. With this graph, I'm proving that the energy is always conserved at all times. And this is one part of the questions in this homework. Energy is always conserved no matter how the other energies are changing. The total sum of those changes in energy is always going to be 0. So the final part of the homework was about importing the data from Tracker and putting this inside the model. So I saved that data in a CSV document, then I called it using Tracker. So we can see here, once again, it will be a little jumpy. But here we can see the red ball moving almost along with the blue ball, which is the one for the model. The motions are very, very close to each other. Because it's a little jumpy, we couldn't see the total motion here, but here I will graph the position, the vertical position in both cases, so we can see more specifically with more. Here we can see the graph. We can see the blue line is the model, the red line is the real motion from Tracker. The motions are very close to each other. We have a very small difference between those two. So we can see that the approximation between the two cases is very close. So the real motion and the model motion are very close to each other. So with this lab, we proved that energy is conserved at all times. We could see the period of oscillation. We can also see that, well, the model predicts very well the real motion that we obtain from Tracker. So thank you for your attention. Goodbye.